Assalamualaikum and hi everyone. Today I'm going to introduce gas chromatography, commonly known as GC. Gas chromatography is a technique used to separate and analyze components in a mixture. This method works best when the components are volatile, which means they can easily turn into gas and their boiling points are different. In GC, we use two phases. The first one is the mobile phase, which is actually an inert gas that flows through the system. This is called the carrier gas and is usually helium or nitrogen. The second phase is the stationary phase, which stays fixed inside a long column. Depending on the type of the GC, the stationary phase can be either liquid or solid. So there are two main types of GC. The first one is gas-liquid chromatography, where the stationary phase is liquid, and the second one is gas-solid chromatography, where the stationary phase is solid. Okay, so now here's how the process works. First, we inject the sample and it gets vaporized at the inlet. The carrier gas pushes the vaporized samples through the column, where the components separate based on how they interact with the stationary phase. Finally, the detector records the signal as each components exit the columns, and this gives us the chromatogram to analyze. So in short, GC helps us separate and detect different components in a vaporized sample using a gas and stationary materials inside the column. So there are four objectives of this gas chromatography experiment. The first one is to determine the retention time TR of N-butanol and 2-propanol. Second, to identify the components present in a standard mixture based on the TR. Third, to identify the components present in an unknown sample. And the last one is to determine the effects of temperature on the TR and RS.
My name is Ain. I will explore the principle and practical execution of gas chromatography, a powerful analytical technique used for separating and identifying chemical components within the mixture. Next is sample preparation. A proper sample preparation is critical to ensure accurate result. The syringe must be thoroughly rinsed to avoid contamination, and the sample volume should be measured precisely at eye level to minimize errors. Any air bubbles present must be removed by gently tapping the syringe, as they can disrupt the injection process and compromise the integrity. Next is instrument configuration. The Agilent 6890 GC system requires careful parameter setup. The oven temperature is maintained at 70 degrees Celsius, while the detector temperature is set to 180 degrees Celsius. This ensures optimal separation and detection. The injection port is also heated to 180 degrees Celsius to facilitate rapid vaporization of the sample. Next is instrument operation. Begin by manually injecting the sample to the receptor. Edit the method by set the title, injection parameters and concentration mode. Select split for high concentration or speedless for lower concentration. Power on the instrument and check the gas level before going online by clicking instrument 1 online and allowing the system to initialize. Next is column configuration. Choose column number 2 with the inlet set to back and the outlet at ambient pressure using constant pressure mode. Save your method under File, then Save mode, and proceed through the setup prompts. For injection, ensure no bubbles are in the syringe. Inject quickly, then press Start. Use the front FID detector for analysis. Last is data analysis. After the run, load the signal via data analysis, then File, then load signal. Create a new calibration table for quantification. Print the calibration document and enter your name in the operator column for record keeping. Proper injection technique, method configuration, and detector selection are essential for accurate result. Always make sure to document your process.
Next, I want to present about result of experiment 5, gas chromatography GC. For the experiment, we want 3 compounds, which is 2-propanol and butanol, and the last one is standard mixture at different degrees Celsius, such as 70, 100, and 140 to determine the retention time. For 2-propanol, we can see that the chromatogram show the peak area is 9.10051 and the retention time is 2.724. Next, move to the second sample, which is N-butanol. This is the chromatography that show the peak area is 161.23991 and the retention time is 2.659. Inside the standard mixture at 70 degrees Celsius, the chromatography show that the peak area is 4.05255 and the retention time is 2.692. Also, from the standard mixture at 100 degrees Celsius, this chromatogram shows two peak areas. The first peak appears at 2.269 minutes and the second at 3.294. For this case, choose the higher peak area because of the higher concentration. And the last one, this chromatogram shows a two peak area from the standard mixture at 140 degrees Celsius. The first peak area appears at 1.952 minutes, which is more volatile if looked early, where the second peak area appears at 2 to 5 minutes.
Determining the retention times of 2-propanol and N-butanol was the first objective of our experiment, where retention time, the duration from injection to detection, reflects how long a component remains in the column and varies based on factors such as boiling point, polarity, temperature, carrier gas flow rate, column length or diameter, and column condition. Using gas chromatography, we found that 2-propanol eluted at 2.724 minutes and N-butanol at 6.43 minutes, with the faster elution of 2-propanol attributed to its lower boiling point and weaker interaction into the stationary phase. It's important to note that the retention times are not fixed. Even on the same GC and column, as small changes in carrier gas flow, oven temperature, or column dimensions can shift the retention time. Therefore, we maintain strict control of all GC parameters to ensure reliable and reproducible retention time measurements. The next objective is to use the retention time to determine which components are present in the standard mixture. The components are present can be identified from the data by looking at the sample's peaks. We can determine that both N-butanol and 2-propanol are present because the retention time is 2.692 minutes and 5.903 minutes for the standard mixture in 70 degrees Celsius. As you can see here, it is 2.692 minutes and 3.294 minutes for the standard mixture that in 100 degrees Celsius, and 1.952 minutes and 2.25 minutes for 140 degrees Celsius. The standard mixture has two peaks and a longer retention duration at 70 degrees Celsius. It indicates that the typical mixture contains two chemicals, with a comparison between 2-propanol and N-butanol. It is evident that the standard mixture is composed of both of these substances. This is due to the fact that the retention times of the chromatograms of 2-propanol and N-butanol are comparable with those of the reference mixture.
Hi, my name is Nurina Atira binti Naseh, and now first I will explain how we identify the components in an unknown sample using gas chromatography. We begin by analyzing two known compounds, which is 2-propanol and N-butanol. These were injected separately into the gas chromatography system at a constant column temperature of 70 degrees Celsius. Each compound produced a single peak with a specific retention time. Next, we ran the unknown sample using the gas chromatography settings. The chromatogram showed two major peaks. To identify the components, we compared the retention times of these peaks with those from the pure standards. The first peak in the unknown sample matched the retention time of 2-propanol, while the second peak matched that of N-butanol. Since both peaks had retention times identical to those of the known compounds, we confirm that unknown sample contains both 2-propanol and N-butanol. Next, we examine how temperature affects two important gas chromatography parameters, which is retention time and resolution. We use a standard mixture containing multiple components and analyze it at three different temperatures, which is 70 degrees Celsius, 100 degrees, and 140 degrees. We observe that as the temperature increased, the retention time decreased. At 70 degrees Celsius, the peaks took longer to elute. At 100 degrees, the peaks came out faster, and at 140 degrees, they elute the fastest. This trend occurred because higher temperature increased compound volatility, making them travel through the column more quickly. We also look at the resolution, which tells us how well two peaks are separated. At the lowest temperature, 70 degrees Celsius, the peaks were well separated, which means the resolution was high. As the temperature increased, the peaks became closer together, and in some cases, they even began to overlap. This caused a drop in resolution. So in short, increasing temperature leads to faster analysis due to shorter retention time, but it can reduce resolution and make it harder to distinguish between similar compounds. Last, for part of discussion, is we discuss how increasing or decreasing the temperature affects retention time and resolution. When we increase the temperature, retention time decreases because the compounds vaporize more easily and pass through the column faster. However, this also causes the resolution to decrease since there is less time for the compounds to separate. On the other hand, when we decrease the temperature, retention time becomes longer. This slower elution allows more time for separation, which improves resolution. The peaks are more distinct, making compound identification more accurate. In summary, if we want high-quality separation and accurate identification, a lower temperature is more suitable. But if we need faster results and are willing to compromise slightly on resolution, a higher temperature can be used.
In this experiment, we determine the retention times of 2-propanol and N-butanol using gas chromatography. We also analyze a standard mixture and identify its components by comparing the peaks with known compounds. Next, we use the same method to identify an unknown sample by matching its peaks with the standard and pure substances. Lastly, we studied how temperature affects the results. We found that increasing the temperature made the compounds come out faster, but it also reduced the resolution between peaks. This shows that temperature plays an important role in both the speed and accuracy of separation in gas chromatography.